Imagine hiring a new employee, right? You look at their resume, and it's just, I mean, it's flawless.
Right, like they're a certified savant.
Exactly. They just won a gold medal at the International Mathematical Olympiad, meaning they can calculate, complex orbital mechanics in their head.
Which is amazing.
You're absolutely amazed. But then you're showing them around the office, and you ask them what time it is by pointing to the analog clock on the wall.
And this is where it gets weird.
Yeah, they look at the clock, they look back at you, and they confidently tell you a time that is off by, like, 3 entire hours. You point to a door, and they genuinely just do not understand how the handle works.
It's a totally jarring paradox.
Welcome to this deep dive. Today, we're looking at the terrifying, sort of fractured reality of the world's smartest artificial intelligence.
Because we really are looking at systems that possess, superhuman reasoning in highly abstract domains, yet they completely lack the foundational spatial common sense of a toddler.
And that is exactly why we're here today. For you, the listener, we are putting on our hard hats. We are acting as forensic engineers today.
I like that framing.
Our mission is to conduct a really rigorous, no-holds-barred, pre-production audit of 2026's absolute frontier AI models.
Right, because we have a massive stack of data here from the 2026 AI Index report.
Specifically, we're zooming in on the technical performance chapter. And I want to be crystal clear with you. We aren't here to read the marketing brochures today.
Definitely not. No cheerleading allowed.
Right. We aren't here to just cheerlead the top-line benchmark scores that the tech giants post on social media, because you're likely considering deploying these models into your workflows, right? Your enterprise environments, or even just your daily life.
And before you do that, we're actively hunting for the fail states.
Exactly. We're looking for the jagged edges, those exact moments where these highly advanced, seemingly magical systems they completely break down.
And, the necessity of this kind of audit really cannot be overstated. If you look closely at the 2026 data, you see a phenomenon that is causing a lot of quiet panic in the engineering community.
Oh, totally. The capabilities are they're accelerating at a pace that breaks historical trend lines.
Right. We're seeing leaps in coding, in mathematics, autonomous agency, things that were supposed to take decades are happening in single calendar years.
But at the same time, our ability to reliably measure those capabilities is it's fundamentally cracking.
Exactly. The tools we use to judge if an AI is smart or safe or even deployable are breaking under the weight of the model's advancements.
So before we even get into what the models can actually do, the hacking, the autonomous coding, the math we first need to forensically examine the rulers we're using to measure them.
Because if we're doing a pre-production audit for you, we can't trust the results if the testing equipment itself is just broken.
Right. And the data from the AI Index shows that the testing equipment is in a state of absolute crisis. It's known in the research community as the smarter than the test problem.
Yeah, to understand the severity of this crisis, you really have to look at how the AI industry has historically measured progress.
It used to be a lot slower, right?
Oh, much slower. For years, the community relied on a standard set of benchmarks like ImageNet for computer vision or GLUE for natural language.
You'd introduce a highly difficult test, and it would take years.
Right. It would take the global research community years to slowly inch the models up from, say, 20% accuracy to the human baseline. It was this reliable marathon.
But now we're seeing benchmark saturation happening in a matter of months. Tests are becoming obsolete almost as soon as they're published.
Take Humanity's Last Exam as the prime example.
I love that name. It sounds like a sci-fi movie.
It does, but it's a real, highly respected benchmark. And it was designed to be exactly what it sounds like, a brick wall for artificial intelligence.
Right. It was constructed to be the ultimate failsafe against this benchmark saturation.
Precisely. The researchers who built it intentionally designed it to favor human experts with deep, specialized knowledge. We are talking about thousands of questions across highly obscure, complex fields.
Like graduate-level physics, niche historical analysis, advanced biochemistry.
Yeah, even human PhDs with open book access struggle with this exam. So the prevailing theory was that this benchmark would serve as a reliable yardstick for the next 3 to 5 years, at minimum.
But the 2026 AI Index report shows that frontier models just completely shattered that timeline.
They really did. They gained 30 percentage points on this exam in a single calendar year.
Which is insane. In 2024, model accuracy on HLE was hovering under 10%. They're basically guessing.
And by 2025, accuracy skyrocketed to 38.3%.
Which compresses the window where this benchmark is actually a useful tool down to almost nothing.
And, when benchmarks saturate this quickly, you lose the ability to differentiate between the top models. It creates this statistical compression at the frontier.
Right. Which brings us to the Arena leaderboard. That's currently the most popular public metric for judging model performance, right?
Yes, it uses an ELO rating system, which is the exact same mathematical framework used to rank chess grandmasters.
I really want to break down how this ELO system actually works for you, the listener. Because people see these numbers and they assume a gap of 10 points means one model is vastly superior to another.
Which isn't the case.
Right. The Arena operates on blind human voting. You put in a prompt, two anonymous models generate an answer, and you vote on which one is better. The winner gains points, the loser drops points.
That is the mechanism, yeah. And the ELO score is ultimately just a reflection of expected win probability. If Model A has a significantly higher ELO than Model B, you expect Model A to win the blind test the vast majority of the time.
But the 2026 data shows a massive performance convergence at the very top. As of March 2026, the four leading AI developers, Anthropic, xAI, Google, and OpenAI, are clustered within a mere 25 ELO points of each other.
Just 25 points. To put that in perspective, Claude Opus 4.6 is sitting at an ELO of 1503, and OpenAI's top model is at 1481.
So that's a 22-point difference.
Which is mathematically a statistical dead heat. At a 25-point ELO difference, the probability of the higher-rated model winning a head-to-head matchup is barely over 50%.
It's essentially a coin toss.
Exactly. If you're an enterprise buyer, you cannot look at a 22-point ELO gap and make a definitive engineering decision that one model is demonstrably more intelligent than the other. They are, for all practical purposes, indistinguishable.
And this convergence isn't just happening among the heavily funded proprietary models either.
No, the gap between open-weight models where anyone can download and modify the architecture and closed-weight proprietary models is razor thin.
Yeah, as of March 2026, the top closed model leads the top open model by just 3.3%.
We are talking about open-source projects running on consumer hardware, closing in on models that cost literally billions of dollars to train.
And the geopolitical implications of that convergence are staggering, right?
Yeah.
For years, the narrative was that massive capital expenditure in Silicon Valley would create this insurmountable moat.
But the performance gap between the US and China has effectively closed. The top US model currently leads by a razor-thin 2.7%.
And earlier in the year, in February 2025, China's DeepSeek R1 briefly tied the top US model on the leaderboards.
When you have multiple companies and multiple nations all hitting the exact same invisible ceiling at the exact same time, it tells you something critical.
Right. It tells you the current paradigm of scaling, just throwing more data and compute at the problem, is hitting diminishing returns, or the tests themselves are failing to capture true intelligence.
Which brings us to the most alarming part of this testing crisis. We're finding out that the tests aren't just saturating, they are fundamentally broken.
The rulers are warped. Stanford researchers recently did a massive, comprehensive review of widely used AI benchmarks.
Let's look at GSM-8K. That stands for Grade School Math 8K.
Right, it's a data set of 8,000 high-quality grade school math word problems. It has been the gold standard for testing an AI's basic logical reasoning for years.
And the Stanford researchers found a 42% error rate of invalid questions in that benchmark.
Wait, 42%?
Yes, 42%. That is a catastrophic finding for the field of AI evaluation.
Okay, I have to challenge that conclusion, though. I hear 42% error rate, and my instinct is to panic. But if every single frontier model from Google, OpenAI, Anthropic is taking the exact same broken test, shouldn't the smartest model still get the highest score?
That's a very common assumption.
Right, because a broken yardstick still measures who is taller, doesn't it? If the test is uniformly bad for everyone, doesn't the ranking still hold true?
It makes sense intuitively, but it breaks down when you analyze what we are actually trying to measure. We're trying to measure reasoning.
Okay.
If a question is logically impossible, or if the ground truth answer provided in the dataset is mathematically incorrect due to a typo, how does a truly intelligent system respond?
I mean, I guess it would point out the error.
Exactly. A model that genuinely reasons through the problem will arrive at the correct mathematical answer, which will then be marked wrong by the automated grader because it doesn't match the flawed answer key.
Oh, wow.
Conversely, a model that has simply memorized the training data, which likely includes the flawed data set itself, will output the incorrect answer, match the flawed key, and be marked correct.
That is wild. So the test actually penalizes genuine intelligence and rewards brute force memorization.
Precisely. When 42% of your benchmark is structurally compromised, a near-perfect score does not mean the model is a math genius. It means the model is incredibly adept at overfitting to the noise and errors of its training data.
And this isn't just isolated to math, is it?
No, the same Stanford study found a 31% error rate in MedQA.
Wow. MedQA, which is a primary benchmark used to test an AI's medical knowledge based on USMLE-style questions.
Exactly. 31% of the medical evaluation data set is flawed.
If you are an enterprise developer building, say a healthcare triage agent, you're looking at vendor benchmarks saying, our model scores 95% on MedQA.
And you deploy it based on that trust.
But if nearly a third of the test is invalid, you have no actual idea how that model will perform when a real human patient describes a complex, multi-symptom condition.
Furthermore, the public perception of model superiority is being heavily distorted by what researchers are calling the leaderboard illusion.
Right. A major study by Singh et al. Recently dissected the ARENA ELO system we talked about earlier.
They found that a model standing on these public, human-voted leaderboards often reflects its adaptation to the platform's specific voting style and user preferences.
It's not a true reflection of its underlying capability. Let's explain how a model games a human voter. Because it's not conscious manipulation, right? It's optimization.
Right. Human voters, especially in quick, crowdsourced environments, are heavily biased by superficial qualities. Well, they prefer longer answers. They prefer answers that use authoritative, confident language. And they really prefer answers that use specific types of markdown formatting, like bolding key terms or using perfectly structured bullet points.
Because the models are trained using reinforcement learning from human feedback, RLHF.
Yes. They quickly learn that if they output a beautifully formatted, highly confident, verbose answer, the human will vote for it, even if the underlying logic contains subtle flaws.
So it's essentially a corporate buzzword generator. The model that wins the ELO ranking is just the one that sounds the most like an overly confident management consultant.
That is a very apt way to describe the leaderboard illusion. It optimizes for the vibe of correctness, not the mathematical reality of correctness.
So if the tests are dead, if the benchmarks are saturated, full of structural errors, or just measuring a model's ability to pander to human psychological biases, how on earth do you evaluate anything for enterprise deployment?
It's the ultimate question.
How does the listener decide which AI model to trust with their company's proprietary data, or their financial operations, or their code base, if the scorecards are essentially meaningless?
That is why we must adopt the mindset of a forensic engineer. Because general benchmarks are flattening into white noise at the top, we have to stop looking at average scores.
Averages hide the anomalies.
Exactly. To understand the true architecture of an AI's mind, we must look at the extremes. We have to isolate highly complex, cutting-edge tasks and simultaneously test incredibly simple foundational tasks.
We are looking for the fracture points.
Yes. And when you structure your audit this way, you uncover the most jarring phenomenon in the 2026 data. Researchers call it the jagged frontier.
The jagged frontier. This is the concept that completely changes how you view artificial intelligence. Because when you look at the extremes, the highs are soaring, like almost incomprehensible highs.
Let's talk about mathematical reasoning, specifically the International Mathematical Olympiad, the IMO.
Right. For anyone who isn't familiar, this isn't just a tough calculus test. This is the hardest math competition in the world, designed to push the most brilliant high school minds to their absolute limits.
We are talking about complex combinatorics, number theory, and advanced geometry that require novel proofs.
To give some historical context, AI has historically been terrible at math.
Very terrible. Language models are fundamentally next token predictors. They guess the next most likely word based on statistical distribution.
Which works great for writing an email, but math requires rigid sequential logic.
Exactly. If you mess up a single sign on step 2 of a 50-step equation, the entire result is wrong. So for an AI to even attempt the IMO is a monumental undertaking.
Last year, in 2024, AI systems managed to achieve a silver medal equivalent at the IMO.
But it required a heavily scaffolded, human-assisted pipeline. The problems had to be manually translated by human experts into a formal mathematical coding language called Lean.
And the system required days of brute force computation to find the proofs. But this year, the 2026 report outlines what happened to the 2025 competition. DeepMind's Gemini DeepThink model didn't just get a silver.
It won a gold medal.
It scored 35 points. It solved 5 out of the 6 problems end to end. And here's the truly terrifying part. It did it entirely in natural language, and it did it within the strict 4.5-hour time limit of the actual human competition.
It's incredible. It didn't need humans to translate the questions into code.
It just read the English text of the problems, generated its own chain of thought reasoning, built an internal search tree to explore different proof strategies, recognized its own dead ends, backtracked, and reasoned through them exactly like a genius human mathematician.
It is a staggering leap in architectural capability. To solve an IMO problem in natural language requires deep, multi-step logical deduction, intense creativity, and the ability to synthesize disparate mathematical concepts in entirely novel ways.
It is the pinnacle of abstract reasoning.
A system capable of this level of self-reflection and search is operating on a plane of logic that 99.9% of humanity will never reach.
You see a result like that, and your immediate instinct is total trust. You think, okay, this system's the super genius. If it can solve novel combinatorial geometry proofs in 4 hours, I can certainly trust it to read a document, pull a date, or manage my schedule.
But then we look at the catastrophic lows of this jagged frontier.
And this is where the AI's intelligence completely fractures. Despite this literal gold medal genius-level math capability, the exact same class of frontier models fails spectacularly at basic, everyday physical reasoning.
We are talking about toddler-level common sense.
The contrast is genuinely difficult to wrap your head around until you look at the specific benchmarks that test visual and temporal reasoning.
Right. There is an evaluation called Clockbench. Its entire purpose is to test whether a vision language model, an AI that can see and process images, can look at a photograph of an analog clock and tell you what time it is.
The clock. The circle with numbers in 2 hands. Something a 6-year-old learns in 1st grade.
Exactly. And on Clockbench, the absolute top-performing frontier model, GPT 5.4 High, reads those clocks correctly only 50.6% of the time.
It is effectively a coin toss whether the smartest AI on the planet can tell you the time. For context, the baseline for an average human on this exact same dataset is 90.1%.
But the data gets even stranger. It's not just that the AI gets the time wrong, it's how it gets the time wrong.
Right. When a human misreads a clock, their median error is usually off by about 3 minutes. You glance at the clock on the wall, you see the minute hand hovering near the 3, and you think it's 4.1, but it's actually 4.15. You make a minor spatial misjudgment.
When the AI misreads the clock, its median error is off by 1 to 3 hours.
Which is just bizarre. And we see the exact same fundamental fracture in a related benchmark called calendar QA, right?
Yes. This tests an AI's ability to extract information from a visual image of a calendar. The models are highly adept at recognizing visual patterns that correspond to major holidays, like if there's a turkey icon, it knows it's Thanksgiving.
But when they are asked to perform basic date arithmetic based on the visual layout, like if today's the 3rd, what date is 3 weeks from Tuesday? They completely fail.
They do.
I need to understand the mechanism here. How can a neural architecture that is sophisticated enough to build a search tree for an international math Olympiad proof fail to understand the spatial relationship of 2 lines on a circle?
That's a great question.
What is actually breaking inside the model?
To understand this, we have to look at how these vision language models process images. When you feed an image into a model, it doesn't see it the way a human eye does. It uses an architecture like a vision transformer, or VIT. The model chops the image up into a grid of tiny squares, usually 16 by 16 pixels. These are called patches. It then flattens those patches into mathematical vectors, lists of numbers, and processes them as individual tokens, very similar to how it processes words in a sentence.
So it turns a picture of a clock into a sequence of mathematical words.
Exactly. Now, a study published in IE Internet Computing did a deep dive into these specific clock failures. They found that the models consistently confuse the hour hand and the minute hand.
Because they just look like lines.
Right. Because both hands are just dark, diagonal lines spanning across multiple 16 by 16 pixel patches, the model struggles to differentiate them in vector space. And once they confuse the hands, their ability to judge the direction those hands are pointing completely deteriorates.
The underlying mechanism here is a critical lack of compositional visual reasoning.
Correct.
Okay, let's unpack compositional visual reasoning. What does that mean in practical terms?
It means the model struggles to piece together multiple distinct visual cues within a single image to form a coherent functional whole. It can look at the image and identify the concept of a clock face. It can identify the numbers. It can identify that there are hands. But understanding the specific spatial and functional relationship between the length of the hands, the angle they form, and the numbers they point to all simultaneously overwhelms its attention mechanism.
It's like having all the puzzle pieces but not knowing how they fit together.
Precisely. And this highlights a profound difference between artificial intelligence and human intelligence. Human intelligence is deeply embodied.
We live in the real world.
Yeah, a human child spends years interacting with the physical world. They learn spatial reasoning by dropping blocks. They learn object permanence. They learn temporal concepts like the passage of time, the movement of the sun, and the structure of a day long before they ever encounter abstract concepts like algebra.
Let alone quantum physics or Olympiad-level mathematics. Their abstract reasoning is built on a massive, concrete foundation of physical reality.
An AI, however, has no physical body. It does not exist in time or space. It is trained on massive data sets of text, code, and static images.
So it can master the abstract symbolic language of high-level mathematics by mapping statistical relationships between tokens without ever once being grounded in the physical reality of how a clock actually measures time.
That is exactly it.
That is a wild visualization. I want you, the listener, to really imagine the danger of this jagged intelligence. Let's bring it back to the enterprise deployment scenario.
Okay.
Imagine you're integrating one of these frontier models into the back end of your financial firm or a medical records department. You run a test to see if it's smart enough for the job. You give it a massive, complex financial modeling equation. Or you ask it to synthesize a dense 50-page pharmacological study.
And it executes the task flawlessly in seconds.
Because it did that, a psychological switch flips in your brain. You implicitly trust it. You project human-like competence onto it, because if a human could do that math, they would obviously possess basic common sense. So you trust this AI to process a scanned PDF of a critical, time-sensitive contract. You ask it to extract the timestamp of when the physical document was signed. But the AI doesn't understand compositional visual reasoning.
It ignores the text timestamp.
Exactly. It looks at the analog clock on the wall in the background of a photo attached to the file, confuses the hour and minute hands, and timestamps your multi-million-dollar transaction 3 hours late. It triggers a cascade of automated legal failures, all because it lacks the common sense of a first grader.
That scenario is the exact risk of the jagged frontier. Competence in one highly advanced domain does not guarantee competence in a basic foundational domain. The intelligence is fragmented.
We're building digital savants with massive catastrophic blind spots.
We really are.
Okay, so if these models have a fragmented, almost hallucinatory understanding of the physical world because they lack embodied experience, how do they handle the purely digital, logical world?
Right, because code is text. It is exactly the medium they were born in.
To find out if they are truly reliable, our audit needs to move from visual reasoning to the very architecture of our digital infrastructure coding and software engineering.
This is a crucial transition for the audit. Coding is where the AI industry has seen the most aggressive capital investment and the fastest rate of enterprise deployment.
Every tech company on Earth is trying to build an autonomous software engineer right now.
And the benchmark data here tells a fascinating story of incredible localized success coupled with significant structural architectural weakness.
Let's start with the successes, because they are undeniably impressive. We have a benchmark called SWE Bench, specifically SWE Bench Verified.
This is the gold standard for testing autonomous software engineering.
It doesn't test the model on toy problems, right? It tests the AI by feeding it real-world software defects and bug reports pulled directly from actual high-visibility GitHub repositories.
Exactly. To succeed on SWE Bench, an AI cannot just write a snippet of Python. It has to navigate the repository, read the execution trace to understand where the error is happening, locate the specific file among hundreds, write the patch, and ensure it passes the repository's unit tests.
It's a highly complex multi-step process, and the surge in performance here is staggering. In 2024, the best models in the world were hovering around 60% of the human baseline on SWE Bench Verified.
By 2025, they skyrocketed to nearly 100%.
Claude 4.5 Opus is leading the pack right now, hitting 76.8% accuracy on the total test. which essentially matches what a skilled human developer could do on those specific bug-fixing tasks.
And we are seeing a parallel surge in a related benchmark called Terminal Bench 2.0. This tests an AI agent's ability to navigate real terminal environments, the command line interface.
It asks the agent to perform tasks like compiling legacy code bases, managing package dependencies, or setting up server environments.
And accuracy on Terminal Bench jumped from 20% in February of 2025 to 77.3% by early 2026.
These numbers are phenomenal. If you're an engineering manager and you stop the audit right here, you deploy these models immediately. You fire half your QA team, you automate your bug triage, and you celebrate.
But this is a deep dive. We don't stop at the surface metrics.
Exactly. We look for the fail state. And in the realm of coding, we found it in a benchmark called Vibe Code Bench.
Vibe Code Bench is critical because it fundamentally changes the paradigm of the test. It does not ask the model to fix a bug in an existing code base.
What does it ask?
It asks the model to build a complete end-to-end web application entirely from scratch, based purely on a natural language prompt. It tests autonomous creation and architectural design, not autonomous repair.
And here, the illusion of full autonomy breaks hard. When forced to build an application from scratch, the top model, Claude Opus 4.6, only achieves a 56.5% success rate.
And it drops off a cliff immediately after that.
Yeah, the next best model is down in the 40s, and the vast majority of the frontier models that scored near 100% on bug fixing, fall below 15% accuracy when asked to build an app.
It's a massive drop.
Why? Why is a model capable of flawless, complex bug repair completely incapable of building a simple web app from nothing?
The mechanism of failure here comes down to the difference between local optimization and holistic architectural reasoning. You have to think about how these models process information within their context window.
The context window is the model's active working memory.
Right. When you give an AI a bug to fix on SWE Bench, you are giving it a highly constrained, localized problem. The architecture of the app already exists. The database schemas are built. The API routes are established. The rules of the codebase are already written.
The model simply has to act as a pattern matcher.
It scans the localized context, finds the anomaly, the broken pattern, and patches it. Neural networks are exceptionally good at localized pattern matching.
But building from scratch is a completely different cognitive task.
Exactly. When you ask them to build an app from nothing on Vibe Code Bench, they have to generate a structural blueprint. They have to write the backend server, the database schemas, the front-end components, and the API calls that connect them.
And as they generate this code, their context window fills up.
Yes. They have to maintain long-term coherence across multiple interdependent files. They have to anticipate how a choice they made for a database schema on step 1 will affect the state management of a user interface on step 50.
As the required reasoning horizon extends, their ability to maintain architectural integrity degrades. They lose the plot.
That's a good way to put it.
Wait, but couldn't the development team just use a vector database and RAG retrieval augmented generation to fix that context window issue? Just let the AI search its own code base to remember what it did on step 1?
RAG is excellent for retrieving factual data, but it is very poor at maintaining holistic architectural intent.
Okay, what do you mean?
RAG can fetch the exact syntax for a React component the AI wrote earlier, but RAG cannot evaluate how changing a database parameter right now will create a race condition in that React component 50 steps later. It retrieves the text, but it doesn't retrieve the causal architectural reasoning.
So what does this all mean for a dev team looking to deploy these models? Let's use an analogy for you. The AI coding assistant is like an incredibly fast, superhuman copy editor.
I like this analogy.
You can hand this editor a 1,000-page manuscript that is absolutely riddled with grammatical errors, misplaced commas, passive voice, and spelling mistakes, and they will fix every single one of them in seconds. Flawless execution. They optimize the existing structure perfectly.
But if you hand that exact same super editor a blank stack of paper...
Right, and you say, write me an original, compelling 500-page mystery novel, the process falls apart. They will write an incredible first 15 pages. The dialogue will be sharp, the pacing will be great.
But by page 20, because their reasoning horizon is so short, they forget who the killer is.
Exactly. The detective suddenly turns into a toaster. The plot logic disintegrates into total nonsense.
That is a perfect visualization of context degradation. They lack the sustained long-term architectural reasoning required for true independent creation.
And this limitation in building from scratch reveals a much deeper, more concerning structural issue about how these models execute long-term goals in general.
Because if an AI struggles to orchestrate a multi-file coding project within a safe, isolated digital sandbox, what happens when we unleash them onto live operating systems?
Giving them access to the open web and real-world infrastructure, which brings our audit to its final and honestly most critical test, agentic AI.
We are moving beyond language models that just answer our questions in a chat interface. We are evaluating AI agents.
Systems designed to take independent action on our behalf in real-world environments.
This is the leap from answering to doing. Agentic benchmarks are designed to test end-to-end task completion in real, messy, dynamic environments. The AI isn't just generating text, it is moving a mouse cursor, clicking on web pages, typing into terminals, and interacting with live databases.
And the initial data here is, frankly, terrifying if you look at the domain of cybersecurity. Let's talk about Cybench. This is a benchmark that tests an agent's ability to autonomously solve cybersecurity capture the flag tasks.
In plain English, it tests the AI's ability to hack systems.
The 2026 data shows that the unguided solve rate for AI agents on Cybench jumped from a mere 15% to a staggering 93%. We have autonomous agents hacking systems with 93% accuracy with zero human intervention.
And we are seeing rapid progress in general computer use as well. There is a benchmark called OS World, which tests an agent's ability to navigate real operating systems.
We're talking about the AI actually viewing a screen of an Ubuntu, Windows, or Mac OS user interface and taking actions to complete a user request.
Right. Accuracy on OS World jumped from 12% to 66.3%. That is closing in fast on the average human baseline, which sits at 72.35%.
And on Web Arena, where agents have to autonomously navigate live websites to accomplish goals like finding a product, adding it to a cart, and checking out performance, hit 74.3%.
It's impressive.
Okay, stop right there. They are autonomously hacking at 93%, and they are using computers and navigating the web at around 66 to 74% accuracy. If you look at those numbers, it sounds like we're on the verge of total societal level automation.
But again, as forensic engineers, we have to look for the jagged edge. Where does the agentic model fall apart?
We found the failure point in a benchmark called TauBench.
TauBench is perhaps the most critical evaluation for enterprise deployment because it tests something that neither hacking nor basic web navigation requires.
Which is?
It tests strict adherence to complex rules during a dynamic, multi-turn interaction. TauBench asks the AI agent to use tools like querying a database or executing an API call while holding a conversation with a human user, all while strictly following rigid corporate policy constraints.
Give me an example of the kind of task TauBench asks the AI to do.
It simulates real-world customer service and operational tasks. For example, a user asks the agent to modify a flight reservation. The agent has to check the airline's database, but it also has to adhere to the airline's complex rebooking rules.
Like checking if the original ticket class allows for fee-free changes within a 48-hour window.
Exactly. Or it simulates a retail environment where the agent has to process a return, but it must enforce a strict 30-day return policy and check if the item falls under a specific electronics exemption category.
And on TauBench, the absolute best model in the world right now, Claude Opus 4.5, caps out at a 70.2% success rate. The rest of the frontier models are stuck down in the 60s.
This specific metric raises the most important question of our entire audit. What is the acceptable failure rate for an autonomous agent? I refer to this as the agentic reliability gap.
Right. When you are just talking to an AI in a ChatGPT interface, asking it to brainstorm marketing ideas or summarize an article, a 70% success rate feels pretty good.
Because if it gets a fact wrong or the tone is slightly off, you just hit regenerate. The cost of failure is zero.
But in end-to-end operational automation, a 70% success rate means a 30% catastrophic failure rate. It means that 3 out of every 10 times you ask the agent to execute a workflow, it breaks.
I want to walk you, the listener, through a day in the life of deploying a 70% reliable agent in your business.
Let's do it.
Imagine you integrate an AI agent into your customer service pipeline to handle refunds. A customer emails in asking to return a laptop. The agent accurately parses the email, polite as ever. It queries the database and finds the purchase record.
But because the interaction requires multi-turn context and rule adherence, the agent's reasoning horizon degrades.
Exactly. It hallucinates your company's return window, it ignores the electronics exemption policy, and it autonomously issues a $2,500 refund to the customer for a laptop they bought 2 years ago.
The agent thinks it successfully completed the task. It marks the ticket as resolved. But 3 times out of 10, it is actively losing your company money, violating HR policies, or accidentally deleting the wrong database file while trying to update a record.
That is the reality of current agentic deployment. But I want to address an obvious contradiction in the data.
Yeah. Why can an agent hack a secure server with 93% accuracy on Scibench, but fail to process a simple retail return 30% of the time on Taubench?
Yes, that makes no intuitive sense.
Hacking requires deep technical knowledge, while a return policy is just basic logic. Why the massive gap?
It comes down to the architecture of how these agents solve problems. The massive success on Scibench is actually a red herring for general business utility.
How so?
Cybersecurity capture the flag tasks are uniquely suited to how current AI models operate. Hacking involves rapid, brute force exploration. The agent can use a technique called fuzzing.
Right, trying a bunch of stuff really fast.
It can try 1,000 different exploits, inject thousands of payloads, and analyze the immediate error codes it gets back from the server. It is a highly parallelized trial and error process with an immediate feedback loop.
So if the agent fails 999 times but the 1,000th exploit works, it hacks the server and achieves a 100% success rate for the task.
But business operations don't allow for brute force trial and error.
Exactly. You cannot brute force a customer service interaction. Following a strict corporate return policy while talking down an angry customer requires sustained context, nuanced judgment, and an unwavering understanding of rigid constraints.
If the agent makes one mistake, if it promises a refund it shouldn't, the entire task is a failure. You don't get 1,000 tries to adhere to HR policy.
Current agentic models simply do not have the architectural reliability required for unmonitored, high-stakes, constrained execution.
They just don't.
Imagine hiring a hyper-caffeinated intern. This kid is an absolute technical genius. They can hack into your competitor's secure server in 3 minutes flat using brute force.
Wow. Okay.
But when you ask them to manage your calendar and book a flight according to the company's travel policy, they get it catastrophically wrong 1/3 of the time. They book you in first class when the policy says economy, or they book a flight to the wrong time zone because they got confused.
Are you going to let that intern run your business operations unsupervised?
Is a 70% success rate actually deployable in a production environment? Or does deploying these agents just create a massive pile of hidden cleanup work for the human managers who have to constantly go back, audit the logs, and fix the 30% of tasks the AI silently broke?
The data strongly suggests the latter. Until we solve the architectural issues of context degradation and constrained adherence, deploying these agents autonomously is a massive operational liability.
Okay, let's pull all of this together. Our pre-production audit of the 2026 frontier models is complete. We've looked at the data from every conceivable angle.
We started with the foundational tools, discovering the profound evaluation crisis. The benchmarks are saturating faster than we can build them.
And the tests we rely on, like GSMAK and MedQA, are riddled with 30 to 40% error rates, meaning we're often measuring a model's ability to memorize flawed data rather than its true intelligence.
We examined the terrifying reality of the jagged frontier. We saw how a model can win a gold medal in the International Math Olympiad, building complex reasoning trees in natural language, yet completely failed to accurately read the time on an analog clock.
Due to a structural lack of compositional visual reasoning, it proves that advanced cognitive capability does not equate to foundational common sense.
We looked at the coding limitations, revealing that models can flawlessly optimize and fix existing bugs at near 100% of human capacity on a WE bench.
But they fundamentally fail to architect and build a new application from scratch on Vibe Code Bench because their reasoning horizon collapses over long contexts.
And finally, we uncovered the danger of the agentic reliability gap. We exposed the myth that hacking success translates to business utility.
Showing that while agents can brute force cybersecurity tasks at 93%, they fail to follow basic corporate policies in a multi-step task 30% of the time, creating an unacceptable liability for real-world automation.
These AI systems are breathtakingly powerful. The leaps they are making are genuinely historic. But they are deeply structurally inconsistent.
They are digital savants with massive critical blind spots. So as we wrap up this deep dive, we want to leave you, the listener, with a final thought to ponder as you look at your own enterprise workflows and automation strategies.
We are currently in the midst of a frantic global rush to integrate these AI agents into our end-to-end processes. We are preparing to hand them the keys to our operating systems, our corporate finances, our medical records, and our security infrastructure.
But consider the totality of the architectural flaws we've discussed today.
If a frontier model, backed by billions of dollars in compute, cannot reliably distinguish between the hour and the minute hand of a simple clock,
And if the very benchmarks we use to test their safety and capability are saturated with invalid data and leaderboard illusions,
are we automating our world faster than we can actually comprehend the blind spots of the minds we are putting in charge?
when you look at your deployment dashboard tomorrow and all the unit tests light up green, remember that the testing equipment itself might be broken. The automated X-ray machine is showing muddy waters. Look closely at the jagged edges of the AI tools you use, because right now that is where the real risks and the real story are hiding.